So John just took me through your lab, tremendously exciting things. But my job here is to, and he's been a very gracious host, is to actually bite the hand that feeds me. So let me tell you the academic scam. In order for him and Dan to get money, he's got to do really cool things that you can't do. They're giant, right? Every paper you publish, we've done the biggest chip, the fastest chip, and that's how he can get money to pay you guys peanuts, so you work 80 hours, so you do these hard things, okay? But the scam I'm going to break to you is when you get to industry, it ain't glamorous like this, okay? So if you're looking towards a very exciting presentation, it's not. It's actually going to be quite boring. But what I'm going to tell you about is if you want to go out to industry and make money, this is what stuff looks like that makes money. So that's a little disclaimer, and if you're getting bored through going through this thing halfway and you leave, I won't take it personally. Here's the outline. One of the things I always like to start out with, I've actually been in a number of fields in satellites and medical electronics. And it's always good to kind of look a little bit outside of your own pond because lots of people have lots of good ideas and there's always something you can learn. And certainly in communications, tremendous amount of innovation that's been going on, for the last 100 years since the telegraph was invented. So I just want to give you some snapshot of mainstream voice band, wireline, and wireless standards. Again, these are the standards that either at the time or now are in high volume and are making lots of money. I'll categorize for you the commercial optical communication business. Again, it's not so much technology partitioned as application partitioned. And I'll tell you about today. What's shipping in the millions? What is every data center? From Google to the smallest guy to UCB, what do people use to actually run the internet? And the internet, of course, except for the last few meters, is all fiber. Then I'm going to discuss, so today it's all 1 gig and 10 gig and actually everything in between, 2, 4, 8, depending on which flavor. Then I'm going to discuss 40 gig and 100 gig, which is the stuff that's getting introduced right now. Actually very exciting. Optics was the field that got the most money in the bubble. So I think that's when most of you were in kindergarten, I think, if I do the math right. But billions of dollars literally were being poured into every crazy idea. And because it was the highest flyer, it crashed the most. I mean, there were companies when the bubble went down that, their sales literally went to zero, like submarine cables. And so the last 10 years, starting in about 2001, which is when the bubble crashed, have been kind of tough. I mean, you had all this overinvestment, too many companies, it was very conservative, and it was really focused on the bottom line. But it's starting to get exciting again, because the internet is growing, and now we're starting to introduce new technologies. So I'll tell you about what's coming out today, what's the future for the next 5 years. I'll give you a little tip, secret tip. If you want to make your fortune, what you should focus on. So I'll when I get to that part, pay special attention. Actually, that's a way to keep you in this thing through here. What I'll do then is I'll kind of look back, and it will all seem very confusing to you because there'll be different bit rates, channels, and you're going to sit there, why did people do what they did? And I'll try to kind of put all that into a context that there's actually a reason behind the madness. And then I'm going to spend some time crystal balling things. What's beyond what's being introduced now, which is 100 gig. So 400 gig and even greater than a terabit. So non-optical datacom. In the beginning, when 70s, 80s, when it was started, it was very simple. It was just a couple of wires, like your telephone wires. Very simple modulation, limited by Nyquist and limited by symbol distortion. Whereas if you look at voice band 10 years later, and still today, you can still buy modems actually. You can still get internet service over a phone line. Wireline, which is anything like DSL or in data centers, and certainly wireless, which is the most exciting. It's really very complex, and there's potentially many things to learn. It's multi-channel in every context, which removes the Nyquist limit because you have many channels. So it's either parallel wires or FDM. Complex modulation, including very complex modulation, where the per channel Shannon limit is approached. The symbol distortion is removed, and obviously it requires very complicated DSP. So let's look at a couple of examples. Kind of the first really interesting communication product. This is the first line is the standard. ITU is an international standards organization. It adopted a standard called V22 in 1980, which essentially copied what Bell Labs developed in the 70s. So there was an equivalent Bell Labs standard, but theirs was called, I believe, 212, some acronym in front of that. And it was really the first successful modem. The bit rate was 1,200 bits per second. And it was already pretty clever because the baud rate was 600, so the modulation was QPSK. So this is, we're talking 30 years ago. One channel, because it was a wire pair which was split into two frequency band, upper and lower, and that was one direction in one band and the other in the other. No DSP. And actually, I started out my career in satellites, but then I moved to IC work, and my first assignment was working on a chip like this, and we had to add a DSP to double the rate to 2,400 bits. That, by the way, tells you a little bit how old I am. So V32, huge jump in 4 years to take the rate to 9,600. The baud rate went up by 4, much more complex modulation. Instead of splitting the band into two, the signal was sent bidirectionally over the full band, so over one wire pair, and you had to have very powerful echo cancellation, right? So signal going from one side. Adaptive equalization, forward error correction. I mean, this is the whole shebang, and we're talking about 1984. Wireline datacom. So again, wireline really means internet. This is the thing that exploded in the 90s. There's a whole bunch of people that made a lot of money on this. They have beautiful houses in the Bay Area now. But when people talk about a lot of what happened in the 90s, it was a combination of these two standards. And then things, switch chips and software that could route this around. So in 95, which is right at the beginning of the bubble, a standard was adopted for 100 megabits per second. And every workstation, every computer had 100 megabits per second out the back. The baud was 125. Bits per symbol were 1, even though a 3-state PAM was used. This is a form of phase cancellation, so this was selected so that successive ones wouldn't interfere with each other. Very simple, so it was 4 wires, 2 wires carried one direction, another 2 wires carried the other. The cables are called CAT. CAT 1, 2, 3, 4, 5, 6. I forgot where this started, probably CAT 3 or 4. And the only DSP was 4B, 5B encoding, which means 20% overhead to basically put in a timing mark and then scramble the data in there. So if you look at this, this is 1995. This is actually simpler than the modems were 10 years before that. Why is that? Because it was good enough and it was cheap. And actually, a lot of computers still ship with 100 megabits out the back. The next standard, which is an incredibly successful standard, it's called 1000 base T. I guarantee you, you have tens of thousands of these links here in UCSB in your data centers. Every computer now has this thing out the back. So we're talking about hundreds of millions of ports. And this is, by the way, dirt cheap today. A chip that does this is a little plastic chip, where the cost of the packaging is probably more than the cost of the silicon, because it's been around for about 10 years. So people have just driven the cost down. But you look at this thing, and it's mind-boggling. The bit rate went up by a factor of 10, but notice that the baud stayed the same. And the reason is that they wanted to reuse all the wires that were put in here. So you went up by a rate of 10, but you reused the same cables. Much more complicated modulation, 5-state PAM, again, somewhat over-modulated to give some good properties. Bidirectional over 4 parallel wires, so look how clever they were here. They took those same 4 wires, and now they're running signal in parallel across 4, but in both directions. Hell of a problem, right? Echo cancellation. You look at the constellation, so trellis coding, you're actually coding across symbols and across all the channels. Very, very complex DSP. And look at the jump. This is 4 years from something very, very simple to something extraordinarily complex. And as I said, hundreds of millions of ports. Every laptop has one of these chips in it. Wireless datacom. Wi-Fi, 11B, again, these are IEEE standards, and these are also IEEE standards. You'll have this presentation, so I'm not going through all the details, just you have reference material if any particular topic interests you. Both of these Wi-Fi standards actually started out very complex. 11 megabits, that's a simplex rate, so Wi-Fi operates one direction at a time. And 11 is probably, that's the marketing pitch, right? If you got an antenna here, no interference. Typically, it's much less. Fairly low baud. Look how complex the modulation is. It's one channel, but the access scheme is very complicated, and the DSP is just through the roof. A is in a higher band, much higher rate. Again, mind-blowing complexity. Now, the one interesting thing here is they use a technique called OFDM to create a large number of channels. And probably in wireless, OFDM is the most powerful signal processing technique. What I don't have here is another wireline or voice band standard, which is DSL, which is the way most people get internet to the home. And that also uses OFDM to create a large number of channels across which to carry information. So what I said at the beginning of the introduction to this section, it's good to look at other areas, right? Because you can learn something. There's a lot of clever people in non-optical areas. Not as many as in optical, but there are. And there's many tremendous ideas here. So if you're looking at coherent receivers, you should always go here and study these things. However, OFDM is one of these ideas where the optics guys have a lot of envy because it's cool. And so they're trying to force fit optics to OFDM. Now, OFDM is a technique which is wonderful for nulls, which you get in DSL or you get it in wireless, right? Because let's say you have that wall here and I'm transmitting to there. You have a direct path and then you have a path which is longer, and if the phases are right, the stuff will cancel out. And depending on how that happens, you can get a very narrow, very sharp null. DSL, same thing, right? You got wires, goes to your home, and you have an extension in the bedroom, and you've got this stub hanging on it. Again, you can get really sharp nulls. So if you have a broadband filter trying to take that out, right, the span of it can be huge. So you have settling issues, whereas OFDM is beautiful for that, right? Because it's just, oh, okay, you just lose that little channels. Great, so we're down to 47. And everything's wonderful. You know, in that case, we would have lost, what, 2% of capacity? Optics, on the other hand, fiber, it's a perverse medium, right? If you wanted to make the life of graduate students miserable, and you actually sat down and said, I'm going to invent a medium to, make you guys stay up till 3 a.m., and you couldn't do a better job than fiber. I mean, it really is perverse. But despite this long list of perversions, the one thing it doesn't have is it doesn't have noise. And so every conference I go to, and every time we get some startup coming into us to pitch their OFDM idea, I always ask them, why do you need this? So anyway, little background there. So anyway, very important, look at other communication areas, lots of things to learn, but also be very skeptical. Just because it's sexy doesn't mean it's useful. Let me give you an overview of commercially how people in the industry look at fiber optic communication. And it's three major areas. Telecom, which is long-haul transmission, like Los Angeles to New York or San Francisco to Tokyo. Shortwave, which has to do with the technology, but it's very short optical links, and then long wave. So as I said, telecom is 100 kilometers, 500, 2,000 kilometers, even 6,000 if it's an undersea cable. It's multi-channel. That was the huge breakthrough of fiber. You can get 64 channels in one fiber. It's 1550 nanometer tunable CW laser followed by a Mach-Zehnder per wavelength, and you can get 64 of these. Right now the standard is that the wavelengths are separated by 50 gigahertz. Very complicated optical amplifiers, dispersion compensation, but notice the links, it's moderate volume. If you have a product, you sell 1,000 of these, 10,000 of these. Now you get a lot of money for it, and you get really a lot of money for supporting it, and the carriers get a lot of money for the service, but the volume is actually modest, right? Because how many of these large links do you need? And the problem is fiber's so good, right? You get 64 channels on one fiber, just don't need a lot of equipment. Performance requirements are very stringent, right? Bits per second per hertz, right? Every tenth of a dB, you sweat because these are very expensive part. If you can double the distance between optical amplifiers and your Verizon, you're cutting the number of optical amplifiers you need by half. Huge savings. Right now, most traffic is 10 gig and lower. It's all serial NRZ. NRZ is on and off keying, so it's sort of, I can use it just with a light. I could signal to the room, in the other building. It's just on and off. 40 gig is really starting to be deployed in very high volume now. 100 gig is not commercially yet deployed, but it's, within a year or two you'll see this thing pick up. And we desperately need it because the backbone is just groaning. I mean, the internet is overwhelming it. And these are both now going to complex modulation. You guys are doing a coherent receiver here, great work. Very heavy use of DSP, but it's cool, sexy stuff, so I'm not going to talk about it. What I am going to talk about is the stuff that's really the money and the high volume. There's just two of them. One is called shortwave. The reason it's called shortwave is because it's 850 nanometers. It runs over multi-mode fiber. Today it's OM3, which is either 62 or 50 micron fiber, and it's used for 10, 100, up to 300 meter reaches. And it connects within racks, so it will connect boards. If you have switching chassis, it will connect those, or it will connect routers to switches, to transport equipment, etc. It's all based around VCSELs, or vertical cavity surface emitting lasers. Finisar has a fab in Texas that makes these things. We're the largest VCSEL manufacturer. I think we've made more than 100 million VCSELs cumulatively to date. By the way, by way of comparison, remember what I told you about the wire, the 1000 base T standard, which is on the back of every computer? That's 100 million every year probably. I don't know how many PCs are sold. So again, it still shows you that wire is the dominant volume interface, but we'll fix that worry. And then the volume of these interfaces per year hundreds of thousands to millions per year. Very stringent cost requirements. I mean, you're always, especially for the shorter distances like 10 meters, you got the purchasing guy going, should I use a copper cable or spend, you know, the 1 gig parts are sort of in the 30, 40 bucks. 1 gig and 10 gig, and I'll talk about it in more detail, are serial NRZ over duplex multimode fiber. 40 gig and 100 gig, it's still serial NRZ, but now multiple channels, so multiple fibers. And this is all orders below fiber, Nyquist, Shannon, you know, the things that bug people in those other 3 disciplines, no concern. And then the second major datacom application is over single mode fiber. Again, point-to-point interconnect. Distances like 2 kilometers, 10 kilometers, 40 kilometers, maybe even 80. Again, in very large data centers between buildings. If you're all the traffic here between the various buildings on campus will run on these kinds of interfaces. And it's all based on 1310 nanometer DFB lasers. And that's why it's called long wave. So shortwave, 850, long wave, 1310, and 1550 is also referred to as long wave in the industry. Again, very high volumes, including millions per year in the 1 gig category. Stringent cost requirements, although typically not as much as for the multi-mode stuff. Apples to apples for the same rate, single mode, because the DFB laser is much more expensive than a VCSEL, will cost 2 to 3 times more. Again, 1 and 10 gig serial NRZ. And now we're finally getting some excitement. 40 and 100 are, it's WDM NRZ again over duplex single mode. And still, Nyquist and Shannon have nothing to do with our life. Okay, let's talk about today. This is where all the money is today. 1 gig and 10 gig, as I said, ships in the millions. So let's look at standards again. You notice IEEE is really big in datacom standards. They write Ethernet standards, and that's the dominant. So these little nomenclature, 1000 base SX, 1000 base LX, refers to Ethernet standards. 1998, so that's smack in the middle of the bubble. When these standards were written, the products were already shipping in high volume. That's typically what happens. The guys writing the standards, they're not doing it out of charity. You know, John gave me a lot of credit, but actually it's selfish because you're writing the standard and you think you're going to get a year or 2 jump on everybody else. Eventually, this is all published, right? Anybody can go on the web, get this thing. But what you're hoping is, as you're writing the standard, you're developing the product, and it gives you a 1-year lead on the other guy. As I said, the shortwave, 850 nanometer VCSEL, 1310 nanometer DFB for the long wave, bit rate 1 gig, baud is 1.25. The reason for that is 8-bit, 10-bit encoding. What that means is every 8 bits you stuff a couple of other marker bits and you scramble the thing. Channels, it's 1 channels, although it's 2 fibers, right? So you use 1 fiber for one direction, 1 for the other, and then NRZ. So this is about as other than this is as brain dead stupid as you can make communications. You know, if I took this out, communications any simpler. Even the telegraph, 150 years ago was actually more complicated because that was a form of pulse width modulation. So, I mean, us optics guys, right now what makes us money is just really, really trivially simple. Now, I have some goodies here to show you. These things are primarily shipped in a module called SFF. So it's a little box like this. If you go to a switching thing, you'll see a large rack of 32 or 64 of these ports. So these are modular. You plug those in, and then for multimode, the convention is to color multimode orange. You get this duplex fiber, and you just plug it into to the end of these modules. And again, I apologize to those that know this. This stuff is just really simple. You can see And then there's another module sitting at the other end, and sometimes you'll have connectors in between. Okay, next one. Okay, 10 gigs, so we're jumping by 10. Remember the date here, 98. So 4 years later, we're coming up with 10 gig standards. This page is just shortwave, so 850 nanometer VCSEL. There was a standard, and by the way, again, remember the way the standards work. People actually first do the work. Often they have products they introduce, and then they try to convince everybody else to adopt it. So when these standards are written, people already have products in the marketplace. So in particular, there was a standard, I have it in quotes because there's certain nuances why it's not a real standard, but we don't need to get into it. We'll say, hey, let's take a lesson from the other guys, and have multiple channels. It makes our life easier. Even though the bit rate is 10 gig, we're going to signal, at a lower rate and have 4 channels by using parallel fibers. Sounds like a great idea. Still the same coding. It turned out this didn't win. One was a serial standard, so very much the same ideas as with the 1 gig, but now 10 gig. So same VCSELs, but 10 times faster. NRZ, two fibers in the same direction. And we thought, okay, if we keep the 8B, 10B coding, people say you guys are really dumb, so we'll make it a little more clever, right? Instead of 20% overhead, it's 1.5%, right? What was the big motivation for that? Well, you had all that fiber installed. So it was just like with the wire guys. If you can reuse the installed fiber plant, tremendous motivation for that. And again, this stuff looks very much like 1 gig. I actually lied before. This is a 10 gig module, not a 1 gig module. It's called SFP Plus. The plus means it can be used for 10 gig. And it's, by the way, a PCBA connector here on the back. You can come up and look at it later. But it's as brain dead simple as you can get. And here is the diagram of the receiver. How does that compare in complexity to what you guys are doing in the lab? 1 VCSEL with a laser driver, 1 pin with a TIA, multi-mode fiber here. 1 type of interface is unretimed, which is actually what that little module is. And then this is connected directly to a switch chip, like a Broadcom switch chip. They'll have 64 10 gig ports on it. Or you could have a retimer. It's a slightly bigger module. I have that here as well. It's called a XFP. Slightly bigger. It dissipates more power, retimes it, but it means this trace can go for a longer distance. By the way, when I used to be in medical and I talked to people, that field has many pluses and minuses, but for lectures, it's great because you put up I would put up ultrasound photos of a baby in the womb smiling or breathing, right? And then I got into this industry, and this is my show and tell. So it's you win some and you lose some. Okay, 10 gig long wave optical. Again, a very similar kind of happened there, which is people thought, actually it was guys from HP, hey, let's make our life easy. Let's run at 3 gigabaud by having 4 channels, 4 WDM channels. It's still duplex single mode. Actually, they could even support multi-mode. And the IEEE even adopted it because nobody could, it's very rare for the IEEE. But they also adopted a serial standard, which is, again, it's just like that standard at 1 gig, except turning the knob up from 1 to 10. And again, the encoding got better. And in the end, this thing won. So, and we'll get to it when I'm going to try to pull it all together for you. So one of the conventional wisdoms, so this is going on now for 15 years, right? This is 1 gig, 10 gig is shipping in very high volume. So one of the conventional wisdoms in the optics industry is that serial or single channel always wins. It's always cheapest. And it's almost become a religion or mantra. And if you try to tell people something else, they say, well, look at 10 gigabase LX4. It was going to be 4 channels and it lost, right? Look at this guy here. It was going to be 4 channels and it won. Serial always wins. We'll see how true that is. And here's a 10 gig transceiver. Again, they're packaged in exactly the same boxes. I'm just going to grab my phone to monitor my time.
The statement you just made, is that still within the context that we're working with in the data center itself, not the long reach?
Well, the long wave stuff with the DFBs will go 10 kilometers.
When in your statement about parallel versus serial, are you constraining that?
Yeah, parallel. Yeah, actually, parallel really from a cost perspective is 100 meters. This standard here, the 10 gig shortwave, both for 1 gig and 10 gig, goes up to 300 meters. Which is the practical limit of multimode. With DSP, you could actually extend it to 400. The reason this makes sense up to 300 is because it's just duplex multimode. Whereas once you go to parallel, the cost basically falls off at 100 meters. Beyond 100 meters, it doesn't make economic sense to deploy parallel. By the way, these modules are standardized. They contain both multimode or shortwave interfaces. So when somebody builds a switch, depending on which one of these things they plug in, you get a different type of interface. You can support a multimode or shortwave or different types of long wave interfaces, but the switch card stays the same. And that's the beauty of modular interfaces. The other one is the presumption is that optics fail more often, which really isn't the case. But and then you can just replace the module without having to touch the whole card. So there's a lot of proposals people are saying, like Intel's been working on that. Let's put the optics on the card. And the reason people don't like that, and maybe it's just a prejudice, is that one of these lasers fails and you've just taken down the whole card. And if it's a 64-channel card, that's a very expensive proposition. So that's another reason why people love these modules. Yeah?
What's your opinion of active optical cable?
Fantastic. It's again, it's very much dependent on the market. So you do the link calculation, 2 transceivers plus fiber versus an active optical cable. You're, depending on who it is, from 30 to 50% less, which is huge, right? 50% is 2x cheaper. So cost is everything in this business. So if it works for your application, it's beautiful. Where does it work? It works in structured environments, like pretty much now all the high-performance computing, supercomputers, use active optical cable. Because when IBM builds Big Blue or something, they just design the whole thing, right? Every cable is laid out up front, so they know exactly every connection, and they actually love active optical cables. Where is it not good? In data centers like here, because you go through patch panels, you upgrade incrementally, so you need different lengths. Active optical cable is one length, right? So where you need flexibility, where you need incremental stuff, that's where you use these modules. So it's application driven, but if you can use it, it's very nice. We have 10G, 40G, and now 100G active optical cables, and we can't make enough of them. So, I mean, this is considered state of the art, by the way. 10G, you know, this is high tech in optics today, and I warned you, you know. Yes.
So what's the estimated price per unit area for the 10G for the long range data?
So 10 gig in a SFP. By the way, here's the single mode fiber. It's again convention. It's yellow. And it is actually thinner because it's 6 micron diameter. And it plugs in very much the same way. But let me pull this out here. But 10 gig long wave module and something like this is under $200 transceiver. All right, so a link will cost you fiber plus actually it's lower. And then the shortwave 10 gig version of this will be under $100. Okay, so next gen optical datacom, 40 gig, 100 gig. In shortwave, actually there was very little controversy. People just said, okay, we're going to finally start using multiple channels. So 4 parallel fibers, 4 in one direction, 4 in the other, and we'll just reuse that 10 gig standard. So this is literally, this standard is like taking 4 of these guys and just plucking them down in one box. Same coding, same everything, no controversy. And here's what it looks like. You have, actually I have one of these prototype modules here. This is called a QSFP. It's actually a mechanical model. And this is a ribbon fiber. So there's actually 12 fibers in here, which is the most common parallel fiber. The real breakthrough is this MTP connector. A Japanese researcher at NTT came up with that, I think in the 90s. And he's here now. He started a company in the US which dominates this and has all the patents. But there are 12 fibers in here. They're mass terminated. They plug into a receptacle like this. You notice 4 of them are not used, so you have 4 of these 10G paths in one direction, 4 in the other. Again, you could have an unretimed or retimed interface. And this is going to be huge. This is just starting to ship now. We're shipping a lot of the active cables, and the transceivers are going to be big.
This patent sits on both sides, so he gets royalties on everything he uses that goes through.
Yeah, MTP. US, it's called US Connect. But brilliant, really, it solved a very tough problem, which is because it basically self-references in the mating. If you look at the design, it appears trivially simple, but it's one of these really clever ideas that revolutionized the industry.
Is the patent scale ordered in 12?
Yeah, these connectors for the same size, you can have, they go in 12s. It had to do with some telecom thing where people like things in a hex configuration, which no longer applies. 1 by 12, 2 by 12, 3 by 12, 4 by 12, and 5 by 12. So up to 60. Although to my knowledge, only 1 by 12 and 2 by 12 are used. 100 gig shortwave. This is actually getting a little bit into crystal ball. What got adopted in by the way, this got adopted last year. So we worked on it and I was part of this effort. We worked on it starting in 2006. It actually took longer than most standards. It got adopted in 2010, but we've been working on products since 2007, 2008. Here's 100 gig multi-mode. And the reaches here for this parallel thing, as I told you, is 100 meters, really. Not because the VCSELs can't handle it, but this parallel fiber just starts being too expensive and too inflexible. Bit rate, 100 gig. The standard that got adopted is 10 by 10. This is, that's why it's called SR10. Again, very simple modulation, but 20 parallel multimode fibers, 10 in one direction, 10 in the other. So in this case, it uses the 2 by 12, right? 2 rows of that stuff. However, this summer, we're going to start working on a new standard, which is called 100 gig SR4, because it's 4 parallel channels, so 4 in each direction, with 25.8 gigabaud modulation. So that will reuse what will become a very high volume fiber. because this 40 gig stuff's going to get deployed in very high volume. All the switches are going to have it. And again, it's much cheaper for 4 channels versus 10. So this is I call it a niche product. We're shipping a lot of it. We love it. All the current supercomputing facilities use this kind of cable. There's some Ethernet shipment. But once this hits the mainstream, this is where you're going to see the real volume.
How accurately do you have to control the length of those fibers?
What do you mean the length of the fiber? Yes. They can be different by very large amounts. There's a next layer above the physical layer. It's called the PCS layer in the IEEE. And you can think of it as IP addressing at the physical layer. What it does is at 100G, it splits up the 100G stream into 25 gig streams and time stamps. It numbers each stream and then timestamps each stream so that they can be actually something like 2000 UI skewed, and then the PCS layer at the other end reassembles the 5G streams into 100G streams and aligns them because they're time-stamped as well. And that's done for free. It's all done in this 66, 64 overhead. So every 10,000 or 50,000 frames, you flip your alignment bit and said, I've got this timestamp and lane number information so that you can line me up. And Ethernet's very flexible. If you drop data, it just retransmits, so it's not an issue.
Are they below that layer physically? Are they still running deskewing up to that point?
So at the physical layer, the beauty of 40 and 100G, unlike the previous standards, is you don't worry about skew. You no longer have to match traces. You no longer have to match fibers. When you have WDM standard, which I'll get to, you get a lot of skew because if the laser temperature drifts differently at different wavelengths, you can get a lot of skew.
So remember, timestamps are sent parallel. Every timestamp entity is sent serial.
Let's see.
If you don't run any.
You have a 100 gig stream, so think about doing a 1 to 20 demux to generate 25 gig virtual lanes. This physical interface here is 10G, so it means 2 of those virtual lanes are running per 10G physical lane. But each one of those 5G lanes is numbered from 0 to 19. So at the other end, that lets you reassemble the streams, sequentially. So you can start reassembling them. And in addition to those numbers, there's a counter that runs. I'm frame 1, 2, 3, 4. So then you can take all those 5G lanes and line them up in time. So when you reassemble the bits, they're 100.
So I guess my question was, for frame 1 itself is sent serial, not parallel. Otherwise, we'd have to deskew frame 1.
You can't. I think what you're saying is 5 gig is the lowest granularity you can have. But serial is the wrong word to use because notice 2 5 gig lanes are actually interleaved here to get a 10G lane. And the thing is set up in such a way, that's why you have 5G lanes, because you can have 25 gig. This is made up of 5 virtual lanes, right? And it's a real beauty. It just says at the physical layer, you don't worry about any of that stuff. And here's what the 10 by 10 looks like. Turns out we make these things in 12 by 12 arrays, 12-pin array, 12 VCSEL arrays. It fully matches to the fiber, and there are guys that want that. Like the supercomputing guys, they want a slightly different rate. So these cables are actually rated 150 gig. And again, you could either retime it or not. But again, it's not terribly sophisticated, right? It's still this on and off keying. We're just multiplying the channels. And this is the thing that's really going to take over the market. And it looks just like the 40 gig guy, right? 4 channels. It uses the same fiber. We're making these VCSELs now. That's really what's going to be the high volume thing. And here's the key technology for 40 and 100 gig. This is a micrograph of our 4x10G VCSEL array, right? So this stuff is shining light out. You bond, I think, to this point and the other connections on the thing. This is on a 250 micrometer pitch, which is matched to the pitch in the MTP array, right? So those parallel fibers, when they come out of this connector here, are on a 250 micron pitch. So you put some lenses over that, but the VCSEL array sits on a flex circuit and shines straight into the multiple fibers, and you do it in parallel. And then you have a parallel laser driver array behind it. So it's tiny. I mean, the whole thing is on a flex circuit. It's 850 nanometers, and if this is 250, obviously that's 1 millimeter. And then our 12 by array is just 12 of these. Oh, well, because this is an academic environment, I knew someone would call me on it. I call it a PIC, you know, because that's sexy. But it's not really a circuit because there is no optical connection. So the components aren't truly connected. So I knew one of the academics here would quibble, so I just put that to cover myself. Yes.
This might be a dumb question.
There are no dumb questions. The only dumb thing is when you don't make measurements. That's the only dumb thing.
So, is direct modulations always preferred in those show data?
That is a conventional wisdom. NRZ is always cheapest.
Okay, so that's the cost concern.
Yeah, it's if you can do the simplest, dumbest thing and somebody pays you money for it, do it. Right? Why work hard? It's like here at UC Santa Barbara, right? Beach and sun. You know, why go to some place like Pittsburgh or Boston, you know, where it's bad weather and.
So there is another name for this optics. It's called dirty optics, right? I mean, literally, that's been the historical. You know,
Dirty? No, I never heard of that. Why?
datacom is what we call dirty optics. Because you
Oh,
noisy,
yes.
lossy,
Yes. Very, very good point. So the advantage of the, well, first of all, you need the multimode fiber for VCSELs because you can't get the vertical light to get into a 6 micron thing. You'd throw away most of the light. So that's one reason. But the really nice side benefit for multimode is when you go through patch panels and you have some dirt and you block half the light, no problem. With single mode, it's much more sensitive to that. If you block that, so it's an excellent point. Reminds me, I didn't fully answer your question on the active cable. The reason active cables are cheaper is that the optical spec inside the cable is entirely controlled by the manufacturer at both ends. Whereas with a transceiver, you expose the optical interface, and it's consequently much more stringent because you have to build in margin because you're going to talk to someone else at the other end. So that's the huge win. You can put VCSELs or lasers in that would flunk in a transceiver.
But if you ever want to upgrade, you have to pull that fiber up.
That's right. And that's why it's very limited, right? Who wants to run 300 meters of one cable? Especially if you know, with the single mode, you've got structured cable, it's all there. You go from 1 gig to 10 gig, you just swap your switch, but you still use the existing infrastructure. Whereas with active cable, you can't do that.
one goes as far as to say, like in a WDM active cable, you could do like the submarine guide where they actually trim the receiver end and active transmitter side and forget out this slacking out.
No, because it wouldn't be cheap. It would be sexy, but it wouldn't be cheap. It would absolutely not fly. This stuff is dirt cheap. I mean, these VCSELs are
So no one's making WDM active cable?
not to my knowledge.
How fast can you modulate those pixels?
So these are 10G VCSELs, and you will see 25G VCSEL products introduced this year. There was another thing I should have said. I actually don't know very much about optics. I certainly don't know anything about lasers. There's a lot of smart people at Finisar that I hang around. So I'll try to mouth some things they've told me, but for forgive me if I get it wrong, because my background is actually circuits, not optics. But it's the same thing, and I'll go through that later. There's a resonance frequency, and it has to do with the band gap energy. So today, I believe we use gallium arsenide, which gives you a resonance frequency around 10 gig. And now we're going to a different material system like indium gallium arsenide, which raises the resonance frequency to something like 15, 17. There are also guys like there's a Japanese company which has a quantum dot VCSEL. I don't know what a quantum dot is, but it sounds pretty good. Their VCSEL runs at 1060 nanometers. And all of this stuff is published. 25 and 40 gig VCSELs have been published in the literature. Company you could search on is VI Systems. And they fab their VCSELs at a university in Europe whose name escapes me right now. But if you Google on that, people have published on that, including the material systems for the VCSELs. But commercially, it's 10G. And then the first products, the 25G VCSELs will look almost identical to this, right? You got to keep the pitch the same because it's the same fiber. But the whole trick is in the material system. By the way, I believe John's invited one of my colleagues, Daniel Megarefte, who actually knows something about lasers. So you can actually ask him real questions. 40 gig long wave. This is another very interesting tale. The first 40G long wave standard was defined, probably it was prior to 2000. I couldn't find the exact date as I was preparing this. Bell Labs defined it. It's now Telcordia. It's called OC768. So that was defined in the peak of the bubble, right? There was no limits to what we could do. Total exuberance, right? And conventional wisdom was serial is the best. And people said, we've got 10 gig. We want to quadruple the speed. Let's go 40G serial, right? This is when I got into optics. This is actually what I worked on. It was like, I decided I kind of semi-retired and it was boring. So I thought, okay, let me get back in. I had some friends who were working on this, and it sounded very cool. And what a miserable problem that was. I mean, talk about banging your head against the wall. We're just finally starting to ship this stuff 10 years later. And I'll get into why that is. Look at that. 10 years later, IEEE comes around, 40 gig standard, and it says, this is a dumb idea. We're going to go with 4x10. So 10 years, so talk about being ahead of the curve here. Anyway, here's what the block diagram, finally starting to look a little interesting. Here's what the block diagram looks for that serial transceiver. You use a device called a serializer or deserializer, so there are actually 16 data lanes here at 2.5G. They're converted to 40G. Modulator is the only way to get that kind of stuff out, and then very simple receiver. When this stuff first started out, so the company I worked at called Big Bear did the first modules like that. Our first modules were 25 watts, and they were 5 by 7 inches. Yes, in the chassis, so things like that. None of these have a heat sink on them, but typically you have a heat sink and people blow air over these things. This can handle up to 3 watts, but and I'll get to that because John asked me to talk about energy efficiency. 10 gig DFB-based part is about 1 watt. Maybe it's actually in an SFF with a CDR it's more. But shortwave part will be maybe half a watt, whereas a long wave part is 800 milliwatts. So when this thing came in at 24 watts, it's like, holy smoke, boy. And it was, when we first started shipping this stuff, it was $35,000 for one of these, right? And what did I tell you? You can buy these. Now, the 10G wasn't that cheap, but you can buy this for under $200. And we'll get into that, why that is. I thought I'd show you some data. This is a 40 GI, and then the typical sensitivity here is -10. And this is what the 40 gig WDM transceiver looks like. Very much like the parallel guy. 4 DFBs, CWDM mux. CWDM means it's 20 nanometer spacing. It's still 1310. So these lasers are coming off the same line that we're building hundreds of thousands of 10G lasers. And here's what a 10GI looks like out of one of these transceivers. Sensitivity is much better because it's 10 versus 40G. If it wasn't for the demux loss, that thing would be somewhere over here. Okay, 100 gig long wave optical datacom. We tried to look ahead a couple of years, and we defined it as 4 channels, so 25.8 gigabaud. So you got 4 WDM channels, still NRZ, a little bit of encoding on it. First generation of parts, which got introduced last year, are EML based. So we basically took that 40G technology, discrete technology, and got some parts into the market because customers wanted it. This year, you're going to see DFB-based stuff, 1310, so off the same line that you get hundreds of thousands of the 10G parts. Here's what the part looks today, the EML-based. Same kind of serializer, deserializer, which takes 10 10G lanes, which is the switch standard today, converts it to 25G lanes, and that looks very much like the 4x. This is called LAN WDM. It's a little tighter grid. It's a 5 nanometer grid, so it puts all 4 wavelengths near the zero dispersion. No, they're indium phosphide. Actually, EML is really the first commercially successful photonic circuit because it has a laser section and an EA absorption section, and it has one connection from the laser to the EA. So an EML is actually a true photonic integrated circuit. And that photonic integrated circuit sells a 10G, probably in the tens or hundreds of thousands. EMLs, it's a couple of volts. The commercial parts that we use, like we don't even make these. We buy these from a Japanese company, same company that makes our 40G EMLs. So the big disadvantage of these guys, one is you got to be on a tech, right? Because you got a laser and you got an EA and the band gaps aren't quite right. So you really can't have the thing floating up and down in temperature. You got to keep the temperature the same. And then the mod drivers chew up a lot more power. Typically, you run them off of 5 volts to get the 2-3 volt swing. And that's the huge advantage of, let me just show you that this is 25G data. It looks remarkably like the 40G stuff because it's the same technology. But that's why the DFBs, the direct mods, are so much better. First of all, you're not throwing 6 dB of power or half the power away, right? 3 dB of power, because you turn the power on and off. And then the laser driver, it's a current device, so you can actually run it off of a much lower voltage. And that's why they're significantly lower power. So this is really what high volume 100G long wave is going to look like. It looks exactly like the 40G stuff. And here's the key technology for 40 gig and 100 gig. High yield photonic WDM circuits. I can't really show you the kind of stuff we have now because it's very proprietary. This is a Psyoptics chip. It's actually neither 40 or 100 gig. It's the chip that was made for that standard that failed at 10G. Remember I told you that 4x3? It's actually for that. That's probably why they're happy to share that photo because nobody's using this anymore. But this is what you need to be in high volume. There are 4 lasers here. I don't know where they are. They're like here or something. And then this is an AWG that combines them into a single output. So now I'm going to give you a tip. If you wanted to make money in datacom, in optical datacom, in the last 20 years, you would have built single lasers and either DFBs or VCSELs. If you came in and tried to do photonic integrated circuits, you would make no money because there is nothing to connect. You have one laser on transmit, and you've got one pin on receive. There is no optical circuits, okay? Now, good news, at 40G and 100G, you can finally start to make money in photonic integrated circuits. This is a photonic integrated circuits. But don't be wowed by the sexy stuff you publish, right? How many elements you have in that fancy thing you just got the world's biggest thing for? I lost a very big number. Hundreds, right? Okay? Don't believe anything John tells you. If you want to make money in PICs in the next 5 to 6 years, 4-element devices. Either either 4-element VCSELs
You're upsetting them here.
or
Because, all the VCSELs and everything we are using is done like in the late 70s.
oh, I'm not saying you guys shouldn't do that here. I'm just telling your students if they want to make money when they go out, don't do what John does because that's for making money 10, 20 years from now. You don't have to hey, it's free advice.
The part about it is like all the guys that stay here don't make the money. These guys all go out and make the money.
Right, but you got to be smart enough to know.
Dinner.
I'll take you out to dinner anytime, Dan. But the guys that make the money are smart enough to know you're not going to make the money with the 1,000 element PICs. This is the sweet spot for the next 5 to 10 years. In 5 years, 4-element VCSELs and 4-element DFB PICs are going to be shipping in the hundreds of thousands. And 10 years from now, circuits that look very much like this will ship in the millions. That's my crystal ball. Now, I may be proven wrong, but also some people say, well, no, it actually is 10 by. That's the sweet spot, okay? And the reason that's not true is that the number 4 is less than the number 8. And once the laser's fast enough, 4 lasers are lower power and cheaper than 10 lasers. It doesn't matter what the speed is. That's why 10 gig is 1 laser, not 4 or 10 1 gig lasers. But anyway, that's my advice to you. You want to make money, make this stuff cheap.
So your comment about serializing is true as long as the driver...
Don't ruin my punchline.
Okay.
Okay?
Well, does that mean we have 50 gigabit modulators? But the answer wouldn't be
Okay.
times 50, right?
1 minute. But good lead-in. Okay, optical datacom. So let's do little optical datacom architecture Q&A. So data rate, as we know, equals number of channels times baud. Baud is kind of an old-fashioned term. We used to use it. I don't think it's used much anymore. Times bits per symbol, where baud is symbols per second. So question number 1. Why do all rates use NRZ modulation? I think you asked that earlier, right? Or you did, I'm sorry. It's because on-off keying is simplest and cheapest to implement. You know, your switch on the wall is on-off keying. Okay, question number 2. Why are 1 gig and 10 gig rates serial? Well, because one channel is simplest and cheapest to implement, right? Well, if that's true, why are 40G and 100G either parallel or WDM? Well, sometimes conventional wisdom bites the dust. Okay, that's the biggest thing you should learn here. Don't trust anybody. Don't trust John. Certainly don't trust me. Don't trust Google, by the way. Don't trust anybody. If there's one thing you should learn here is always go back to fundamentals. The only thing you can trust are a good measurement and a good analysis. This is PowerPoint. Oh, that's the other hint. The thing you should distrust the most is PowerPoint, by the way. So I believe I'm rephrasing or paraphrasing what you just said, John. Minimum number of channels at the max baud that is simplest and cheapest to implement in the technology, in mainstream technology, mainstream laser technology, mainstream IC technology, which for the foreseeable future results in more channels than 1. In fact, the sweet spot is 4 channels, and I'll show you why. Will faster rates, meaning above 100 gig, use modulation other than NRZ? Right? Somebody asked me today, is that always going to be true? guaranteed that conventional wisdom will also bite the dust. So to your point, I'm glad you guys are doing this research because we'll desperately need you in 10 years from now. So actually what Dan is doing is extremely useful despite how much I give him grief over it. All right, how do we determine max baud to know min number of channels? Oh shoot, I'm actually running over time.
I want to know the answer to that question, so that's all right. Go
Okay.
over time.
By the way, thank you, John, for telling your students they got to sit here through my lecture because they'd probably all be leaving now. Okay, let's take a reference. I don't know, some of you guys may know the guy, Larry. Laser process figure of merit. By the way, I didn't know this stuff. I had this big shootout with a guy from Google at ECOC, which is this conference in September. So I had to up on this stuff. So I grabbed Larry's book, very nice book. And he's got this laser process figure of merit called FR, relaxation resonant frequency. And it's, basically the gain of this curve, the difference in the currents, I guess that's a square root sign, and it's also temperature dependent. So you go to all the fabs in the world. You don't go to one. You certainly don't go to a small one, but you go to all the mainstream guys, Finisar, Opnex, Sumitomo, Mitsubishi, there's actually way more fab capacity still in the world that you need. And you ask them, what is the FR of your mainstream laser production processes? It means they're qualified, they're reliable, not, some guy producing a one-off device. They've run thousands, tens of thousands of these devices through accelerated lifetime, and it's going to work there flawlessly like a copper wire for the next 3 to 5 years. Max baud is about FR times 1.5. Okay, why is that? Well, max baud should be no higher than basically the low pass bandwidth of your laser, right? And then Professor Cauldron says that the 3 dB bandwidth is FR times 1.55 if you equate these two things. F peak is a laser peak response frequency. I read that in September. I actually don't remember what that is anymore. If somebody asks, I think John could help me out with that. And the other thing here, this assumes that fiber dispersion is not a limit. So clearly for the long haul stuff it is, but in the datacom it doesn't matter. Let's see how that works. 2002, 2004. If you went to all the mainstream guys could actually ship you lasers, said, what's the FR? About 9. Some guys were 8, some guys were 9, depending how they did it. 10 gig is less than FR times 1.5. 10 gigabaud lasers were efficiently implemented. Given that you can do that, there's no premium for a 10 gig laser. Why would you build 4 lasers? By the way, 40 gigahertz is FR times 4.5, which is why 40 gigahertz were not feasible. Look what those standards dummies did. They defined a 40 gig serial standard even though you couldn't build lasers. Nuts. Okay, let's fast forward to 2008, 2009 when we were writing the 100G and 40G standard. FR is 17 gigahertz now. Again, not just Finisar, but all the mainstream guys if you look at the publications. Why is that? This guy got better, so the slope's higher, and then they've gotten more reliable, so we can actually run it at a higher operating current. So it's not tremendous progress, and you're really actually working very hard. 25 gig is equal to FR times 1.5. So you'd really like this to be a little higher. Like notice at 10G we've got more margin, but it's doable. And so 25 gig lasers, you can implement them very efficiently today, and you're going to see product introductions. Notice that 40 gig, you can do them. You actually see research papers, but it's actually hard, right? Because now a significant portion of your signal gets attenuated. Okay, SiGe IC limits. So typically what happens, SiGe, which is silicon germanium, has bipolar transistors, which means you can have much faster transistors at a larger feature size than CMOS. So what typically happens is the fastest circuits will start out as bipolar, and then CMOS catches up. Reference, Paul Gray, Robert Meyer. This is the classic reference on analog circuit techniques, 77. Small school up north in the area I'm in. IC process figure of merit, FT, which is the transition frequency. That is the unity magnitude short circuit current gain. That's how you measure it. It's defined in terms of the measurement. But basically, you've got some beta, which is the current gain, and it just falls off to 1. And where it's 1, that's f sub t. So again, you do the same thing. You go to the mainstream guys. You go to IBM. You go to Rockwell at the time. You go to ST Micro, and you say, what FT can you support? And then max baud is about FT divided by 10. Why by 10? Well, because all IC communication blocks need gain. Laser drivers, CDRs. If you have 10x gain, excess gain, it's real easy to make those circuits. At 3x gain, it gets very hard. To build up gain, you got to cascade them. One transistor, another, and each one is biased with a lot of current. At 1x gain, you can't do it because you have no gain. Again, this assumes signal integrity across the board is not a limit. Let's see how that works. Back when we defined 10G, FT of mainstream processes was 110. That was for 250 nanometer SiGe. So the feature size of the bipolar, or actually the CMOS in that process was 250. Sweet. 10 gig is a little bit less than FT over 10. That's why you could do easy SiGe 10 gig parts, and in fact, the first ones that came out were made in SiGe. 40 gig, T over 3, you can do it. Boy, is it hard. Boy, do you burn power. This is what I worked on when I first got into optics. My goodness, that serializer device is 18 watts. Fast forward, SiGe, 220 gigahertz again. ST Micro, IBM, Jazz Semiconductor. You know, IBM's a little faster. I think they're 240. Look at that. 25 gigabaud is about FT over 10. Real easy to make circuits. And sure enough, we're showing SiGe circuits at 25 gig in this process. Notice that 40 gig, you're starting to make your life easier, but it's still not fast enough. And finally, CMOS. I'll probably stop with 4 and a terabit because I'm running way over time, so I apologize for that.
People can leave.
Okay, yeah, feel free to leave. I'm running over time. I prepared this in the last minute, so too much material. I apologize. Tom Lee, he's up at Stanford, very nice guy. Design of CMOS radio frequency integrated circuits, really nice book. Full of very, very dry humor, my kind of humor, so it's worth buying that book just for that, even if you don't care about CMOS circuits. IC process figure of merit, again, F sub T. We're going to use that because it's convenient, it's easy to get. Actually, in CMOS, if you're going to do RF circuits, the unity magnitude power gain is much more useful. It is harder to get, though, because it depends on process parameters like the resistance of the gate. So we're going to stick to FT because you can call somebody up and say, what's your F sub T? By the way, just kind of a quickie rule of thumb, if you have short channel devices, which means you got saturation effects, the electrons can't go any faster, F sub T is inversely proportional to the gate length, and this approximation works okay. Max baud, again, F sub T over 10, same reason, gain. 10x gain lets you do it. Now here where the difference between CMOS and bipolar comes in, right? In bipolar, the F sub T, they're both the same. It's GM over the either base to emitter or gate to source capacitance. But in bipolar, the GM is much lower. Right? The F sub T is the same, but they're about an order of magnitude different. So in CMOS, it's very hard to cascade stages. So 3x is really not doable. Before you can start doing anything that's not impractical, you need 10x gain. So that's the big difference between CMOS and bipolar.
You can really get 10 terahertz out of a 1 nanometer gate length.
Well, I mean, this works for, 130 down to 40 nanometer. I mean, this is approximation upon approximation upon approximation. I didn't even use that approximation here. I just, came up with the F sub T as quoted. But that's easy. 10 terahertz is easy to remember. At 1 nanometer, you'll have 10 other effects that will make it right? It used to be for very long gates, the f sub t was going up as the channel length squared, right? So then the short channel effect, made it harder to improve f sub t, and I'm sure there'll be something else that will come in. It'll be the square root of the L, and then whatever. Okay, let's see how that plays. So f sub t, 120 gig for 90 nanometer CMOS, roughly in that time frame. Hey, look at that, 10G circuits again, piece of cake. And sure enough, by the way, these years are a couple years after SiGe. So after the first generation of SiGe stuff came out, 10G CMOS IC started hitting the market, and it just went off because 8-inch wafers, the stuff cost nothing. And 40 gig, you basically couldn't do it in CMOS because f sub t over 3. So you could do it in bipolar, you couldn't do it in CMOS, and so it was very expensive. Fast forward, 40 nanometer CMOS, mainstream, so that's designs, TSMC released design kits last year. F sub t over 10, 25 gig. Guess what? Every communication IC company, every one, because I talked to every one, is designing 25 gig circuits. 40 gig, some people are doing it, but it's very hard.
So are you saying that the new 50 gigahertz standards that might be coming out for light peak, are they going to be expensive? Because
No, I think light peak is four channels. So the 40, so it's 4 by. Yeah. So it's actually very inexpensive, right? Did that answer your question, John? You were asking. Okay, quick crystal ball. By the way, most technology predictions are wrong. Almost all of them, right? I mean, the famous one was, my famous one was a guy that invented Ethernet, Metcalf, yeah. He said wireless will never happen. The reason is the same reason as you have plumbing for running water in your house. So, and that's a very smart guy, right?
there was a president of Bell Labs who said 45 megabits per second was the maximum water needed in fiber.
Yeah. And they said that integrated circuits never work because, you've got a defect density, and so you have 50 transistors, and so your yield just goes to hell, right? Forgot that they're correlated, but that's why Bell Labs never got into integrated circuits because, one guy, there was a guy that ran the group that, Shockley and all those guys were in, so he was brilliant in promoting that work, that solid state makes a lot of sense, and then he blocked integrated circuits, right? Because he said, for 50 transistors, the defects will kill it. Conventional wisdom, just deadly, deadly. All right, what do people want beyond 100 gig? Meaningful data rate increase, right? They're choking. That's why Google's giving you tons of money. That's why IBM or who else is giving you tons of money? Tons? Maintain parity with 100 gig. Oh, okay. With 100 gig cost, right? We're going to drive the 100 gig cost down. This is a lesson I learned very painfully on 100 gig. These guys want a free lunch. They don't. That's what you'll find out. The end users, the guys that run the internet, they want you to work for nothing. They want optics engineers to develop the stuff so it costs nothing. Actually, their ideal scenario is if you could maintain the compensation you have as a graduate student when you move on to industry. That's what Google would like to do. That used to be, that Cisco is still that way. Yeah. Well, we'll have our last revenge. What do we want? Well, we're making huge investment here, so we want to leverage it, and then this thing's going to be ramping up like crazy. I told you, if you do a good 4-by chip, you're going to sell millions of them in 10 years. So the next data rate should really be based on 100G technology. The way 40 gig is based on 10 gig. Remember I showed you what a no-brainer it was? It was just 4 10G channels. So 400 gig meets these requirements because today we have the technology to do it. We're just scaling it. 1 terabit doesn't meet it. It really requires huge R&D. That's why you guys are getting the big bucks because we will need it for 1 terabit. Lots more money. Yep. Yeah, so I'm not against you guys getting lots of money, it's just we don't have it to spend on that. Okay, so I'm going to propose a 400 gig baseline transceiver. I'll explain to you guys why, but I know how to do this. When I get my VCSEL yield enough, if I put 16 of them in an array, you saw the 4 by array, we make 12 by. I just need to make a 16 by array, run it at 25G, and that's 400 gig, right? So there's nothing here other than 4x from what we're doing today. Now I need a slightly new connect 2 by 16, but hey, we talked to the guys that have all the patents, they're ready to do it. As soon as there's demand, they're going to do a 2 by 16. If you're running 25G channels, there you go, 400 gig up to 100 meters. By the way, for computer buses, that's perfect, right? So they're very excited because if buses go optical, they would sell tons of this stuff. It's TCT. That's the guy that invented the MTP. Basically, you got 2 pins that align, and you see 2 holes here. So in a 2-row thing, you would have 16 receivers and 16 transmitters, and these are on 250 pitch. Yeah.
So here's a standards question for you. So you mentioned early technology. Other companies compete. Is there a standard for this where they just have to pay licenses?
Well, there is no standard. There's just a design. This stuff is referenced by standards, but there's no way to get around paying them. That's part of why this is expensive. And it's a good thing. I think that's the way it should work. You come up with a great idea, and you ought to be able to earn a living from it. WDM, again, no-brainer, right? All I have to do is put 16 of these DFBs, bigger mucks. If I want to keep the same reach, I probably need something like an SOA in front because these are very lossy. 1 to 16, 1 to 10, it's a lossy thing. But hey, I know how to do this. The only thing is I got to get the yield right? Because we're going to start out with 4 by and 16 by. You got to get the yield right. By the way, when I talk about yield in datacom, 60, 70, 80, 90% to make money, right? I'm sure a lot of people heard of a company like Infinera, right? Very, very cool circuits. I mean, they're just down the street from us. But their yield could be single digit. I'm sure when they started out, it was a fraction of percent. But they sell a huge system around that chip, right? It's a completely different order of magnitude.
Sorry, another question.
Yes, sir.
When you guys have to start oversampling your DFB lasers?
No, this is the same laser.
Are those arrays?
Yeah, this would be an array. So it's just like, remember what I showed you here?
So you're getting a high enough yield
Right?
on a 16 DFB array?
No, that's what I said. That's the one thing you have to do, right? So today we get great yield on single lasers, right? The next step is for us to get great yield on 4 by lasers. And the only thing required, which we don't have today, but that's how, you grind at that, right? You hire lots of engineers, and they sit there and they drive the process to improve the yield. We know how to do that.
So back in the days when like Chung and Zod did that famous work at Belcourt on the very first WDM arrays, him and TPU did these calculations. They figured out like a 2x oversampling got you about 99% yield. So you end up with twice as many lasers, right? 2 of each color.
By oversampling, what do you mean?
2 of each color. So that if one dies, you can just throw the other one.
Excess devices.
Excess devices. So if you have
Can you give me that reference? I know nothing about it. I'd like to dismiss it out of hand because I don't understand it, but
Well, so let's say on an 8 wavelength system, right? We back then the devices were not as good as
Right.
an 8 wavelength system. You want to push the chip out, and if one laser dies, the whole chip's going to go, right? So they did a calculation of how many of each color do you have to make, so if one died, you turn the next one on. And it turns out 3 was too many. 2x got you 99% reliability. And that the question is, are you guys looking at over?
no, because we've done all these calculations. We know what we have to do to get the kind of yield you need to have. Yeah, no, please do. But I'm just saying the beauty of 400 gig is I don't need to do tricks like that. Our Fremont guys, our Texas guys know how to drive the process for 4 by and in 5 years 16 by arrays. But for a terabit, believe me, we'll need tricks like that.
So Dan, I've done that calculation, and the problem when you go full factor of 2, cost kills you, right? So you can look at what yield you need to make the most thing. I think the answer here is something more like 18 out of 16, maybe. 2 extra wavelengths, something like that.
Yeah, but then you got to switch them, you got to detect them. In Ethernet, no, but see what people don't like is like just even the switch over in Ethernet you don't want. But please send it to me.
It's like an AP10B.
Decode physical. It's like physical AP10B encoding. Wow.
What's the spacing for
I love straight men. So here's a lambda specification, 100 gig. Here are the 4 wavelengths for 100 gigs. So it's 13, 10, 05, 30. This is round numbers. These are the exact, right? And if we were to do 400, and this is our proposal. This is not accepted by anybody, but it's the same grid as 100G. You would add 2 bands for shorter wavelengths and 1 above.
what spacing was that?
It's about 5 nanometers. It's a little less. Yeah, it's 800 gigahertz to be exact.
So by the way, on the 16 DFB wavelength, that's what you'll see Sid in the afternoon.
Oh, okay.
That's what Sid's making, 16 DFB wavelength.
Sweet. Very sweet. Yeah, so if you were to do it, I mean, a lot of thought went behind this grid, right? It wasn't an accident. It's far enough away that you don't get any mixing products. It's close enough, certainly for 4, that you don't need esoteric processes to build different lasers. So that's alternative 1. So I've put up a crystal ball, and I told you, all technology predictions basically are wrong. So why am I doing this? To expose people that I'm a fool. Most people know that already. Real value is it's a benchmark, right? It's very linear thinking. It's brute force. So if you guys have a better idea, I have a benchmark against which to measure it, right? That's the value of those 2 proposals. Very likely it won't happen that way, but I know how to do it. I know what the power is. For the unretimed version, 16 wavelength, it's about 20 watts. I know how big it is. I can tell you everything about it. And those numbers, people that end product are not happy with it. It's too much power, it's too costly, and it's too big. They've already told us that, okay? But there's the benchmark. And if you come up with a better idea, you better be better by at least a factor of 2 than that. Now, one possible better idea is to do amplitude modulation, so PAM4. Because you can, with PAM4, you can still use lasers, direct mod lasers, right? It's 4 levels, probably some moderate DSP. It's very hard to really keep these levels. Very likely the 100G backplane standard, which is being adopted by the IEEE now, could very well be PAM4. So you may actually get a lot of CMOS silicon and experience in that area. Complex yeah.
I'll argue that won't happen. I think it's easier to integrate an EAM with the laser than it is to do that by a long shot.
Could be.
At temperature.
Could very well be. Here's my benchmark. Show me it's better than this.
I meant the PAM4. By the time you do that and you lose, obviously, length and
Well, CSNR is not really your issue for shorter links. Like if you were to say make it less than 1 kilometer. But could be right. And actually, as I said, all technology predictions are wrong. So to me, the only important proposal is this, not because it will necessarily happen, but because I know how to judge ideas like yours. Complex modulation, absolutely not. There is nothing there that can be commercialized for this application in the time frame of interest. No way. Terabit. Here's a couple of comments on terabit. If there's 400 gig, what's going to be the next rate? Well, terabit is one possibility, but that's a pretty small increase from 400 gig. It's only 2.5. So if you're going to make this huge investment, right, complex modulation, all this stuff, just to get 2.5x is not terribly satisfying. And if people start deploying 400 gig, doing lag on 400 gig, then this isn't going to satisfy anything. Okay, maybe 1.2. Well, 3 is still a small increase for 400. Probably still not likely to justify it. And then 3 is an odd number, which people don't like. So maybe 1.6 for 4x increase. This would probably be the minimum to justify an investment. What?
Landscapers like 3.
Who would like?
Landscapers like 3.
Oh, landscapers. Okay. Maybe you could get some funding from them. I know you've hit everybody else up. They probably make more money than optics guys do. So again, here's some, here's what it ain't going to be. It ain't going to be 64 25 gig NRZ lasers, right? That's crazy. It ain't even going to be 32 50 gig PAM4. So what it's for sure, right? It's got to be complex amplitude and phase. Again, nothing's there today, and that's why, to your point, that's why we need you guys, okay? Excellent opportunity for huge academic research grants, right? Huge. All right. Sorry to keep you here so long. So summary, mainstream interfaces up to 10 gig, single channel, NRZ, just need high-speed ICs and high-speed lasers. Brain dead. 40 gig, a little more interesting, multi-channel, and I'm predicting it's 4. That's the sweet spot. So write that down today. I told you how you could be multimillionaires. Quad laser picks, okay? Who? Yes. Versus 10 by?
What's the bet?
Well, this is saying that it's going to be 4x and 400.
4x for 100, yeah. 4x will be, 4 by 25 will be the dominant, and for 40. 40 gig will be 4 by 10G, and 100 gig, 4 by 25G will ship in the hundreds of thousands as the dominant interface. 5 years from today.
I agree with that.
How much?
He usually bets against everybody.
I bet all the time. I bet all the time. I bet all the time. Who saw the movie Graduate? Dustin Hoffman. Remember that scene? The guy goes, plastics. Okay, quad lasers. Okay. Beyond 100 gig, 400 gig, very likely. I think it'll be very conventional. Whether it's 16 channels or 8 channels, I don't know, but I think we'll find a way to get one last gasp out of VCSELs and DFBs. And then beyond that, you guys better come to our rescue because we have no clue. We have no clue. Yeah.
Back to the energy. You're all about quad direct modulating lasers.
Yes.
I haven't been talking much about modulators.
So, yeah, there is. And John asked me for that. I thank you for reminding me. So here's the problem. Basically, a DFB laser, when you add the laser driver, when you add the retiming, is about a watt. Maybe 800 milliwatts. I mean, maybe 3/4 of a watt. But basically, it's in that range, right? Multimode is not going to work anymore because it's 100 meters or less. All these data centers are getting huge. If anybody have seen, photos of these large data centers, they're massive. I think they refer to them as barn-scale computing. So that's the problem. That's the real problem here. We're talking. Watt is conservative. Let me use it in round numbers, right? 16 channels, that's 16 watts, okay? So even more so than complex modulation, the biggest challenge, the single biggest challenge in the optics industry is how we get the per channel power down with new devices. How can I have a 1/4 watt 10 or 25G? How can I have 1/10 of a watt and the thing is going to go a kilometer? Doesn't have to go much more, but this need was filled by VCSELs before, so the very high density problem, right? The VCSEL over fiber like this is duplex multimode at 1 gig and 10 gig can go up to 300 meters, and that was the size of the data center. So that covered 99% of your needs. VCSELs are very low power. The threshold current is an order of magnitude. The modulation current is it's like 8 milliamps versus 60 milliamps, 50 milliamps, right? So that's why VCSEL, and they're dirt cheap, right? You actually inspect, when you have a wafer, you can inspect, just by looking at it at the wafer level. You mark out the bad ones, and so everything you build is good because you've pre-tested it before you packaged it. Fantastic technology, low power, but it's running out of gas. It just doesn't have the reach, right? It will still be huge volume because inside the racks you're going to keep using multi-mode, but to go beyond 100 meters, this thing is too power hungry. So if you guys want a real challenge, give me a DFB or the equivalent of a DFB or a modulator that's a 1/4 watt or a 1/10 of a watt. That is the challenge. Forget 1,000 transistors. Give me 16 or 4 of these devices where each channel is a 1/4 watt.
The second time we've heard that in 3 days, we have a proposal we'll tell you about over lunch.
Awesome. Thank you. I thank you for your patience.
All right, thank you. Been very patient.
Yeah.
So, give Ray a
Or if you want to see the goodies.
Exhaustion has set in.
Yeah, I apologize.
Maybe it was not to be attentive, but when you went from telephony of 40 gigabits standard to the
Yes.
IPP standard, you changed from 1550 to 1310.
Yes.
Why are you changing this?
So that was another dumb thing, right? 1550, 20 picoseconds per nanometer of dispersion kilometer, right? So you're killing yourself with all this dispersion. 1310, much lower dispersion. So they should have done 13. So not only did they screw the rate up, they screwed the wavelength up. But, I think what happened, they're all human institutions. I think Alcatel-Lucent, who's very influential, Lucent, who was very influential at the time, it was their heyday, said we could make 1550 devices. We could make 1550 photo receivers, but not 1310 at 4G. And that's how the standard was picked. It was a disastrous